Okay, so there are a couple functions that we are going to find the derivative of. They're pretty general, and they're going to be added to our library of derivatives. So see here that I've added all of the trig functions that we talked about last time. This one was the comprehension check question, so you can double check that that's the answer that you got. Okay, so the first function that we can differentiate now that we have the chain rule is e to the kx, where k is a constant. So here, a non-zero constant. So non-zero constant. And if k were equal to 0, we would just get e to the 0, which is 1, and that would be covered in the constant case, right? So we're dealing with e to the kx, where k is non-zero. And so what we can do is use the chain rule, where our inside function is k times x, and our outside function is e to the x. And then we know that the derivative of the inside function, this is just a constant times x, so it will be just that constant when we take the derivative. And then the derivative of the outside function, this is one of our basic functions, it's just e to the x. Okay? Now we just apply the chain rule. So remember that we get the derivative of the outside function right here evaluated at the inside function. So we're going to get e to the kx, and that is the first piece. And then we multiply that by the derivative of the inside function. So that's k. So usually we write constants in front, so I'm just going to rewrite this as k e to the kx. So what happens with this case is it looks kind of like the power rule, because you see that that number that was up in the exponent comes down, but then we don't change the exponent at all. So it stays e to the kx. We just get one of those, a copy of that k coming down in front, right? Okay, so just to have a more concrete example, I guess I have some room right here. So this is, if we were to have e to the 2x, that would be 2e to the 2x, the derivative. Okay, so let's go ahead and add this to our table. So the derivative of e to the kx is equal to k, e to the kx. And now that we have this formula, we can calculate another derivative that we weren't able to calculate before. So maybe I'll use a different label, so g of x. And this was the exponential function where we had an arbitrary base, right? So b was greater than 0. And not necessarily equal to e. So we were able to compute this for this particular value of base, but we couldn't compute it for any other value. And now what we can do is, maybe I'll separate this. What we can do is we can rewrite b as e to the natural log of b. Okay, so remember that e and natural log are inverses, so if we take e to the natural log of something, it will just be equal to that something, right, because they undo each other. So what we've done is rewritten it in this way that's going to help us compute the derivative. So once we do this, then let's see, we have g prime, or let's rewrite this first. So our function is b to the x. When we rewrite b in this way, we get e to the natural log of b to the x. And remember that from our exponent laws, we just multiply these two things together, and in the exponent we get natural log of b times x. And remember, natural log of b is just a number, so this is just a constant. So we can use that rule that we just found to write this as, using the derivative rule, so we just get a copy of that constant down in front, so we get a natural log of b down in front, and then e to the natural log of b x. And remember that these undo each other, so what we want to do now is rewrite this as b to the power x, right? So we're just undoing that step that we did in the beginning. Okay, so that means, in fact, I'm going to drop these parentheses. We get that the derivative of b to the x for an arbitrary b is natural log of b times b to the x. Okay. And then notice that if we were to check that this formula works for the base e, the one base that we were able to compute, we would see that we would get, I'll just write this here, natural log of e times e to the x, which natural log of e is just equal to 1. So we do get e to the x. And so this is consistent with the other formula that we have, right? Okay. So we have two more functions that we can take the derivative of. Now, okay, the next problem is thinking about the chain rule, hopefully in a way that makes it make more sense, because so far it's just been formulas and maybe they're not so intuitive, but maybe, or hopefully this example will help you think about it in a way that will help you get a handle on what's going on. Okay. So the idea is that Crystal works in sales, and every week she makes $400 plus $50 for each sale that she made that week. The longer she works in this job, she gets better at making sales. And so her weekly sales are modeled by this function right here. So she starts off at t equals 0. She made 3 sales in a week in the first week. And then as she keeps going, she makes more and more sales over time. Okay, so how is her weekly pay changing over time? Notice that for each week, she's going to make 2 more sales over that period. So each week, she makes 2 more sales, and for each sale that she makes, remember, she makes $50. Okay, she makes $50 more, right? So that means that each week her pay increases. So let's write each week her pay increases by 50 times 2, or $100, right? Because she makes 2 more sales per week, and each time she does that, she earns $50. Okay, so we can also interpret this using the chain rule that we just learned. So if we were to say that her weekly pay is P, right? We could write down the formula because we are told exactly what it would be right here, but we actually don't need that. We just need to know how it's changing, right? So in our first solution, we didn't use that she made $400 plus $50 for each sale. We just used the part where she makes $50 for each sale, right? Okay, so notice that her weekly pay depends on the number of sales. So that was modeled by this. So this depends on S of t. And so what we get is, using the chain rule, dp dt is equal to dp ds, right? And then times ds dt. And dp ds, that's how her weekly pay is changing with respect to the sales. Okay, so that's what this notation indicates, right? So her weekly pay is increasing by $50 for every sale that she makes. So that's where we get our 50 from. And then her sales are increasing. So we can just look at this function here and see that, where did I put this? I'll just put it up here. Okay. So this is just a linear function, so we can just use the power rule, and this is just equal to 2. Or you could just notice that it's a linear function, so the derivative is equal to the slope. But in any case, we get s prime of t is equal to 2, so that's the same as this ds dt, just different notation, and we get 50 times 2, so 100. Okay, so we can see that we get the same solution. Here we just labeled things and used the chain rule, and in the first case we just can tell using common sense. So this is a simple example where you could figure it out using common sense, but the chain rule applies to much more complicated examples, and you can think of it as a generalization of what's going on here, right? Okay, so we will do some more examples in the next video. Okay.